All right, let's talk about load reflections. Now, up to this point, we've been kind of thinking about transmission line in a somewhat abstract sense, where they apparently just kind of go on forever. But obviously, in practice, a real transmission line is going to have to terminate eventually, and something is going to have to happen at that termination. So maybe there's just, say, an antenna here at the end of my transmission line, or I could just chop it off and leave it as an open circuit. I could short the leads together to create a short circuit, or I could even have some lumped collection of resistors and capacitors to create a lumped load. But whatever it is over here at the other end of the transmission line, that is simply called the load. It's just a generic term for the thing that I'm trying to send energy to or to deliver power to. So what'll generally happen is I have a voltage source here on the left, and it's going to excite some sinusoidal voltage, and it's going to want to propagate from the left to the right. And it's going to run into this load eventually after some propagation delay. And usually some of that energy might get delivered to the load, but in practice what will also happen is some of that energy is going to bounce back. So we tend to think of this as the incident wave over here, and this is the reflected energy, or the reflected wave over here. So all I'm going to do now is just write out the expression for a superposition of a forward and reverse propagating wave, which will look something like the following. V naught plus e to the negative j gamma z plus v naught minus times e to the plus j gamma z. So you have some generic forward propagating wave plus some generic reverse propagating wave. And you notice we're referencing 0 as here at the load. Now, another thing we're also going to do is we're going to make the lossless assumption. All right. So you recall that gamma generally would be some complex value, which we would write as alpha plus j beta. But if we're doing making a lossless assumption, then this alpha term here is going to be 0. And all we're going to be left with is this. Oops, sorry, these j's aren't supposed to be here yet, because that's where that j comes from here. So I'll have a gamma z. So the real part will reflect an exponential decay, and the imaginary part represents phase here. So what will happen now is with no loss, I get the j beta here. So it's going to look like the following. V of z is equal to b naught plus e to the minus j beta z plus v naught minus e to the plus j beta z, where beta, the phase constant, is equal to omega times the square root of L prime C prime. Okay, and all this you can just derive from the propagation constants. Okay, so now remember also, if I have some voltage here, I am not free to arbitrarily specify the current. There is only one current that can correspond to these voltage waves here. So I'm going to write that, I guess, right here. So I of z is equal to, and remember, we learned that from the characteristic impedance, it was going to follow a very simple expression, v naught plus over z naught, like so, times e to the minus j beta z. So that's the current amplitude. And then for a current traveling to the left, I would have to have a minus sign, like so. V naught minus over z naught, e to the plus j beta z, like so. Okay, so given this voltage, this current necessarily has to go alongside with it. All right, so you imagine a voltage here, and then of course, on top of that, there's a current and another current going the other direction. So there is a forward propagating voltage slash current with a reflected propagating voltage slash current. So forward and reflected here. All right, so the question now is, how do I calculate this reflected term here in terms of my incident amplitude that excites the system? So it's because presumably I know what the generator is, and I might know what the energy is that strikes the load, and supposedly that information is all I need to know to figure out how much gets delivered and how much gets reflected back. So how do I solve that? And the answer is very simple. We know that right here at the load, there is a voltage and a current. right here. There's a V/I. And by Ohm's law, that implies, some current going into this little load here that has to obey a very simple equation. So we just write the following. ZL, the load impedance, is going to be V of 0, V tilde, divided by I tilde of 0. So again, this is simply Ohm's law in a nutshell. So the total voltage divided by the total current is, by definition, whatever the impedance is here at that load. All right, so all I'm going to do is just plug in 0 for Z and see what happens. So you look here, I've got a Z, e to the j beta Z with a plus and a minus. Well, if I put in a 0 there, these exponential terms all go away. So you imagine that goes away to a 1, 1, 1, 1, and I'm just left with all of these little terms here. So what I'm going to get is the following. V naught plus V naught minus divided by V naught plus over Z naught, right, minus V naught minus over Z naught, like so. Which, if we do a little bit of factoring of that Z naught, I'm going to get the following. V naught plus V naught minus divided by V naught plus minus V naught minus. If I factor out this 1 over Z naught kind of term, a bunch of stuff simplifies and I just get a Z naught like so. Okay, so now what? Well, all we got to do is think about this for a second. I know that I have a load impedance, I have a characteristic impedance, and I have some incident and reflected waves that kind of are buried into this term here. So what I want to do is kind of rearrange my terms a little and calculate my reflected wave in terms of the incident wave here. So just remember this is equal to ZL. So just look at that and say, I want to solve for this term here. You notice there's 2 of them, so it's going to be a little bit of algebra. And presumably you've done this before in your previous class, 3300. So we're not going to get too bogged down. All we know is algebra will happen. And this will lead us to the following result. V naught minus is equal to ZL minus Z naught over ZL plus Z naught. So the details of that is pretty straightforward. You can do the math if you really want to, but it's 3 or 4 tedious little steps times V naught plus, like so. Okay, so this just directly follows with a little bit of rearrangement here. Okay, so this is the expression we care about. Given a characteristic impedance and a load and some excitation, I can now calculate my reflected wave amplitude. But even this isn't quite what we're usually interested in exactly, because it's much more instructive to think about things in a more abstract sense. And that is to say, I'm not really going to care about this term or that term. What I really care about is their ratio. So what I'm going to do is define a coefficient called the reflection coefficient. So I'm going to just divide out that V naught term there, that V naught plus. And this is, by definition, uppercase gamma, which is called the reflection coefficient. Reflection coefficient. Okay. So this is a very, very important term. So let's just write this out here again. ZL minus Z naught over ZL plus Z naught, which is essentially, by definition, the reflected amplitude divided by my incident amplitude. And I want to put a box around this because this is going to be kind of one of those bread and butter equations that is going to occur time and time again and tell us so much about transmission lines. So burn this on the inside of your memory, or burn this into your memory if you haven't done so already. Or I oftentimes like to say, inscribe it on the inside of your eyelids so that every time you blink, you see this expression, because this is going to just come up time and time again. Now, a little bit of an afterthought here. We're just going to do a little bit of substitution here, because now I know what my V naught minus is as a function of this guy. So if I do a little bit of factoring and rearrangement, you'll also get the following, where V tilde of Z is going to be V naught plus times e to the negative j beta Z plus gamma e to the plus j beta z. So this is what happens when you just kind of take this little gamma term here and you just kind of plug it back into there, because now I know what this term is in terms of that, and everything comes out nice and neat. So you see, given some excitation, I have all of my fraction of my amplitude, in a sense, in my incident wave, and then there's this gamma term here representing my reflected wave. So you can see how it's kind of pulling this term kind of off to the side when you start thinking about it in terms of this gamma. And then likewise, I'm going to say I of z is equal to v naught plus divided by z naught. And I get e to the minus j beta z minus gamma e to the plus j beta z. So just, again, plugging into this term up here. And so that's a nice sort of general way to think about what happens when I excite a load along a transmission line with some voltage. Now, one more thing that I just want to leave you with is the idea of what would it take for all of my energy to get dumped into this load here. Because, for example, if this is, say, an antenna, then reflections are a bad thing. I want all of my energy to get into that antenna and radiate out into space, or maybe it's some kind of heating element, right? As there are many instances where this reflected wave is bad, and I would like to minimize it somehow if that's possible. So if I want gamma to be 0, how do I make that happen? Well, you just look at this equation here, and you notice that if I just set this thing equal to that thing, I'll get a 0. So the condition for no reflection is I just have to set my load equal to my characteristic impedance, like so. So this is where you get the idea of what is called a matched load. In other words, the load is matched to the characteristic impedance of the transmission line.